Ralph Waldo Emerson famously said, "A foolish consistency is the hobgoblin of little minds, adored by little statesmen, philosophers, and divines." Well, he was certainly right about one thing. Consistency has been adored by philosophers, especially philosophers of science in the 20th century, an adoration shared by physicists who, like their philosophical counterparts, sought to take all of the work in 20th century physics and create a single coherent structure, a grand unified theory, a theory of everything. Indeed, we can see this celebration of unification as a running theme throughout intellectual history. William of Ockham is the name most associated with the principle of metaphysical parsimony we see explicitly stated in Aristotle. This principle has been called Occam's razor. All else being equal, prefer the demonstration that employs the fewest hypotheses. In other words, when we're using science to redefine reality, what Aristotle meant by the word demonstration, then, if everything else is equal, that is, if you have two scientific theories which account for all the same phenomena, we should think that the theory that posits the fewest elements to reality is likely the one that's true. We often hear it phrased as, prefer the simplest explanation. By that, we do not mean simplest in the sense of easiest to understand, rather having the fewest assumptions about what sorts of things are real. Reality, according to Aristotle and Occam, is elegant, contains no more things than it needs. So, when deciding between two possible accounts, the better one is that one which puts the least amount of furniture in the universe. This sentiment just refers to the metaphysical aspects of scientific theories. A similar principle holds true in terms of the explanatory power of scientific theories. William Whewell was a scientist. Indeed, he was the person who first coined the term scientist. He also wrote important works in the history and philosophy of science at Trinity College, Cambridge, in the first half of the 19th century. In fact, he was one of Darwin's professors there, and his views greatly influenced the structure of Darwin's arguments. Whewell held that a significant mark of a true scientific theory is what is termed consilience. That is, the ability to bring together results and to make predictions in fields of science other than that which the theory was created to explain. See, scientists are bright people, right? They find classes of phenomena they want to explain, and they come up with theories to do so. Since scientists are so smart, it shouldn't strike us as remarkable that their theories work most of the time. That is, they come up with intellectual constructs that explain exactly what they were designed to explain. There's little fuel for confirmation there, Whewell argues, because the theory is just doing what it's designed for. But when a theory designed to explain A is suddenly also found to explain B with no significant additions to the theory, when B was nowhere in the scientist's mind when deriving that theory, that gives us reason to think the theory is true of the world. Good scientific theories, Whewell argues, simplify science. They bring together what seemed like different fields into a single explanatory scheme. Successful science, true science, is unifying science. René Descartes in the 17th century pointed out that we prefer buildings that were constructed from plans developed by a single architect to those that were built piecemeal. When a building has been added onto and added into, strange features emerge, right? Stairways that lead to nothing, hallways that don't quite meet from different directions, odd dead ends. But those built from a plan developed by a single mind have a coherence and elegance that we admire. The intellectual edifice of our knowledge, he contended, should be similar. And he sought to rebuild all of human knowledge in a clear, systematic way. Indeed, his famous dictum, "I think, therefore I am," is the justification for the first absolute truth, the existence of the self as a thinking thing. That he would use in his project. He would go on to apply this unifying project outside of philosophy when he developed what we call analytic geometry. Now, before Descartes, we thought that mathematics was comprised of two distinct areas, one that dealt with numbers and equations, arithmetic, algebra, and another that dealt with shapes and space, geometry. We thought that these were completely distinct concerns with their own rules, results, and methods, but Descartes did something incredible. He figured out that we could translate shape talk into equation talk, that we can graph lines and circles and describe their behavior, not just as Euclid did with word-based propositions, but numerically. This unification of mathematics allowed us to create equations of motion for complex trajectories of real objects in real space and opened the door for modern mathematical approach to physics. This was inherited by Newton, who extended Descartes' analytic geometry in the creation of his mathematical theory of fluxions, now called calculus, which was used by its co-creator, Newton's rival, the German philosopher, physicist, and mathematician Gottfried Wilhelm Leibniz. But we know Newton's name much better than Leibniz's, in part because Newton used his fame and power to try to destroy Leibniz, but also because of what Newton did with the calculus. He created a scientific theory that replaced Aristotle. Now, recall that Aristotle had one scientific theory for terrestrial physics, right? One based on the natural places of the four earthly elements, earth, water, air, and fire. And he had a second theory for astronomy based on the nature of the fifth element, ether. Aristotle believed that physics and astronomy dealt with different substances, and so they were different sciences that required different sorts of accounts. But Newton gave us three laws of motion and a law of universal gravitation. The important word here is universal. Newton's law of gravitation applies to everything. The story of Newton and the apple? It comes from Newton himself, and most likely is apocryphal. The idea is that he was at home on his farm when Cambridge had been shut down because of an outbreak of the plague. He was sitting under an apple tree looking up at the moon. He was wondering what kept the moon in its orbit when all of a sudden an apple dropped from the tree in front of him. Right, the idea that the apple hit him on his head, that's a later development, right, that was used in commercials. But seeing the apple fall to the ground in front of the moon, he came to realize that both phenomena were caused by the same force. Newton unified physics and astronomy into one single study of nature. His combined theory of mechanics and gravitation became celebrated, Whewell contended, because it was a grand example of consilience. It explained phenomena from astronomy, the falling of objects, the tides, and so much more. Newton was great because he unified science. Similarly, James Clerk Maxwell, in the middle of the 19th century, changed how we saw the universe by taking the separate laws that were discovered to hold for electrical phenomena and those discovered to account for magnetic phenomena and brought them together into a single coherent account. This single account showed that electricity and magnetism were just flip sides of a single coin, that what we thought were two completely separate aspects of reality were just different expressions of a unified picture of reality. It got even better when it was shown that light was to be understood in this way as well. Optics was thought to have nothing to do with either electricity or magnetism. But here was one coherent approach that showed them all to be interrelated in a way that simplified the underlying picture of reality. It made the universe a more elegant place by creating a single theory that unified our understanding of the happenings within it. Recall that Einstein had similar motives at the start of the 20th century, when he found himself dissatisfied in 1909 with his theory of relativity because it lacked an organic place for gravitation. This lack of unity is what, in part, fueled his obsessive search for a general theory of relativity. Nature had to be compact. It had to be unified. And if the theory did not display that, then the theory needed to be changed. This is what brought Einstein ultimately to his field equations, according to which space itself is curved. Now, Einstein's work spurred two very different movements in scientific unification. The first came from a group of philosophically minded scientists and scientifically minded philosophers who came together in the wake of the theory of relativity to try to do what Descartes had done in the first scientific revolution. They wanted to develop a unified picture of human knowledge coming out of the new scientific developments. This movement had one group in Vienna called the logical positivists, who were led by Maurice Schlick. Schlick was the first philosopher who was also a trained physicist. He studied under Max Planck. and he approached the underlying meaning of the theory of relativity. Einstein read and adored Schlick's work and stayed with Schlick and his family whenever he visited Vienna. The second group went by the label logical empiricists. They were centered in Berlin and led by Hans Reichenbach, who was one of the 8 students to take Einstein's very first course on the theory of general relativity at the University of Berlin in 1919. Now, these thinkers were committed to a unity of science, a view that goes back to Auguste Comte, the founder of sociology in the 19th century. According to Comte, the sciences develop in a definite order. First mathematics, then astronomy, then physics, chemistry, biology, and finally sociology. For Comte, this progression is necessary because each new science requires the tools and knowledge from the last. The logical positivists took this one step further and argued that what we have is not just a scheme about the historical time development, but a logical relation between the sciences. Chemistry, for example, is an interesting subject unto itself, but underneath, it's really nothing but physics. Chemistry is done as chemists do it now, not because chemistry is an independent science from physics, rather because the interactions of chemicals are such complex physical situations that we cannot yet work with them in purely physical terms. Similarly thought, biology is just complex chemistry. Life forms do not have a non-material soul. They're just incredibly intricate functioning chemical systems, right? Take a fruit fly. Remove everything from it that's not a chemical. What's left? Nothing. Biology is nothing more than very complicated, choreographed chemical reactions. But chemistry is nothing but physics, and so ultimately all of biology, they thought, reduces to physics. Human psychology? It's to be understood biologically. And once we get more adept, the study of the human mind is just chemistry, and eventually we'll see that the workings of our minds are just physics. This unification is developed through what we term reduction. We don't have separate realms in the study of the universe, but all of them are just more and more complex instances of a single underlying science, the most basic science, physics. Physics and physics alone tells us what is real. What is the furniture of the universe? And the other scientific disciplines exist as separate sciences only because we're not yet able to fully reduce them. But the future of science is one in which we progress step by step towards a fully unified scientific understanding of the world, and thereby the underlying picture of reality we receive from it. This picture of science and human knowledge gave rise to one of the 2 main branches of philosophy in its contemporary form. It's what we call analytic philosophy, and it directly derives from the first attempts to make sense of the philosophical ramifications of the theory of relativity. The other branch, which is largely hostile to the foundations and methods of analytic philosophy, is what's come to be called continental philosophy, and was launched by the mathematician and philosopher Edmund Husserl. Husserl argues that all meaning, all sense of reality must begin with human experience. That we are incapable of speaking about anything objectively, anything from a perspective that is not rooted in human experience. The logical positivists are doing their best to create absolute knowledge, independent of the particulars of human consciousness. But Husserl contended that it's only our internal experiences that we have as the basis for anything we think we know. A student of Husserl, when he was teaching at the University of Göttingen, was Hermann Weyl, who dabbled in philosophy but went on to become an important figure in physics. He opposed the positivist reductionist project. That sort of unification of human knowledge was wrong-headed, but he did see unification as crucial to the advancement of science. As a result, he was the first person to attempt to develop what we now call a unified field theory. Now, Einstein is given credit for the discovery of the general theory of relativity, but it could equally well be called the Einstein-Hilbert theory. David Hilbert is one of the greatest mathematicians to ever walk the face of the earth, and his best friend was another genius, the mathematician and physicist Hermann Minkowski, who was Einstein's professor in college. Minkowski's mathematical reformulation of Einstein's work is what opened the door to the general theory of relativity. Minkowski died before progress was made, but as Einstein did the work, so did Hilbert. The final formulations of the field equations for the general theory were published first by Einstein, but there is reason to think that Hilbert may have found them first. Hilbert was always clear in giving credit for the theory to Einstein, but the historical case is more complex. Now, Hermann Weyl received his PhD under Hilbert for work in mathematics that would be applicable to physics. He'd been thinking about non-Euclidean geometries and the mathematical fields they employed. Remember we discussed what Einstein did in the general theory of relativity was to take gravitation from being a force between two bodies and made it the interaction of mass and energy with the underlying space. Space became malleable, stretchy, curving and bending based upon the distribution of stuff in it, and dictating to that stuff how it would move. The way to determine how much space is curved is to compare the orientation of unit vectors. Okay, a vector is an arrow, and a unit vector is an arrow that is 1 unit long. Place the arrow in a spot in space so that it's pointing straight up according to someone who's standing at that spot in space. Now, allow the arrow to move around the space such that an observer at every new point it occupies fixes the arrow so it points straight up according to him or her. Now, if we were on a sphere and starting at the North Pole, the arrow would be pointing straight up as we normally think of it. But as we move away from the pole, the arrow would turn because straight up changes for the people at different points. We can determine the amount of curvature in a space by looking at the angle between the arrow's directions at different places. This was how we thought about the curvature of space-time field for Einstein. But Weyl realized that along with this gravitational field, this undulating space-time underneath reality, physicists also employed a second field, the electromagnetic field. Weyl's suggestion? Maybe we ought to take William Occam's suggestion and create a theory that took these two fields and made them into a single field, a theory with a unified field. Weyl very cleverly figured out how to fold the electromagnetic field into the gravitational field. Right? Vectors have two elements. The arrow has a length and a direction. If we compare the angle at different points to tell us about the gravitational effects from the field, maybe we should vary the length according to the electromagnetic contribution of the unified field. Compare the arrow at point 1 and point 2. The change in angle tells us about the gravitational effects, and the change in size tells us about the electromagnetic effects. A unified field theory with a single metaphysical element underlying our observations. Beautiful. Einstein's reaction to Weyl was disappointing, but interesting. At first he raised some technical objections, but when Weyl answered them, showing that Einstein's worries were unfounded, Einstein still dismissed the project. Not because he thought it was wrong, but because he thought the world was not yet ready for it. He told Weyl that it was an idea whose time had not yet come. Indeed, Einstein thought the idea was exactly the recipe for the advancement of science, and he spent his own final years looking for such a unified field theory. However, with Einstein's rejection of quantum mechanics, he set off to research in a direction different from the trajectory of the rest of the field. While Einstein was trying to unify the gravitational and electromagnetic fields, the real action began in the quantum field. Recall that once we had a sense of how atoms work, we were left with 4 forces, right? Gravitation and electromagnetism are the 2 we see in the greater world. But then we needed the strong force to keep the nucleus full of positive charges bound together, and the weak force to help create the other subatomic particles. A universe with 4 basic forces seems elegant enough. But not the physicists, right? Why 4? The idea was to try and see if there's any way in which these seemingly quite different forces were really just different ways of seeing the same mechanism in different contexts. Just like James Clerk Maxwell in the 19th century, when he demonstrated that electricity and magnetism were 2 sides of the same theoretical coin, theorists in the mid-20th century were trying to unify forces as well. Americans Sheldon Glashow and Steven Weinberg and Pakistani physicist Abdus Salam were able to do just this in 1967, when they showed that the electromagnetic force and the weak nuclear force were different instances of the same thing. All right, there's 2 out of 4, right? So recall that forces are transferred by the exchange of particles called bosons. For the electromagnetic force, this is carried by the boson we call the photon. The weak force is transferred by a particle called W, which is quite different from the photon in important ways. Glashow, Weinberg, and Salam hypothesized the existence of a second boson for the weak force. That is, a second type of particle which carries the weak force, a particle they called Z. And this hypothesized Z would be a sort of middle ground between the photon and W, more like W in some respects and more like photons in the other. If this were true, then we can show how the electromagnetic force and the weak force could be thought of as the same thing, because this new Z particle would be the bridge which at extremely high temperatures, the sort of temperatures we haven't seen since just after the Big Bang, would cause the photon and the W to collapse together. If the Z boson was real, then photons and W bosons were just different flavors of the same underlying force. Experimental physicists at CERN, the big particle accelerator in Switzerland, were able to produce both W and Z bosons in the 1980s, but not before Glashow, Weinberg, and Salam were already given the Nobel Prize for the idea in 1979. The missing part from the picture that Glashow, Weinberg, and Salam produced was the Higgs boson. So, complete confirmation would have to await its discovery, also at CERN, in 2012. So, we now see 2 of the 4 unified and have a universe in which there are 3 active forces. But these 3 are not seen as a trio, more like a pair and a third wheel. The combined electromagnetic and weak force, now called the electroweak force, and the strong force are part of the standard model and come from a quantum view of the universe. Gravitation is described by Einstein's general theory of relativity, which has a fundamentally different view of the universe than quantum theory. Indeed, the 2 have deeply conflicting elements. Relativity is classical in that every measurable quantity has a unique value at every time. Quantum theory is modern in that there are not absolute values for all observable properties at all time. Relativity theory is deterministic. If you have full knowledge of the state of the universe at any time, this will uniquely determine the state of the universe at any future time. Quantum theory is indeterministic. There are observations whose results we can at best determine to a probability, but cannot determine with absolute certainty. The relativistic world is smooth, where the quantum world is chunky. The underlying realities pictured in these 2 theories are radically different. But there's only one universe, and so the hope is that we'll be able to find some way to unify the 3 remaining forces in a way that creates a single, coherent, elegant structure to reality. Reasonably, this has been thought to be a process that would proceed stepwise. Right? Since the electromagnetic and weak forces have been unified, the next candidate would be the strong force, thereby completing a quantum world synthesis. Such a combination has been given the name Grand Unified Theory, GUT, or GUT, since it's a unification of the non-relativistic elements. A theory which then brings together the elements of the Grand Unified Theory with gravitation is what we refer to as a theory of everything, TOE, or toe. So, if you happen to hear physicists talking about their guts or toes, you'll know the conversation is not exactly anatomical. Now, great press has been given to a potential theory of everything, which is known as string theory. In an attempt to not only unify the electroweak and strong forces, but also include a quantized picture of gravitation. Now, if it's true, it would give us a completely new and exciting, if not strange, new image for our universe. Now, to get a handle on what's happening in string theory, let's go back to the good old pre-quantum days when Weyl came to Einstein with the first attempt at a unified theory that joined gravitation and electromagnetic fields. Now, around this time, others were thinking along the same line. The German physicist Theodor Kaluza proposed a picture that was subsequently developed by the Swedish physicist Oskar Klein. According to the Kaluza-Klein model, we could bring gravitation and electromagnetism together if the field underlying reality was not 4-dimensional, but 5-dimensional. If we add a dimension to the world, we can create a working mathematical model that seems to have all of its features. It's puzzled physicists and philosophers alike for centuries why space has the dimensions it has. Right? If you want to join lines perpendicularly together, you have to stop at 3. Right? We have a 3-dimensional space. Events are located at places in this 3-dimensional space at a time, which has but a single future and a single past. Time is 1-dimensional. Bring them together as Einstein did, and you see a world that is 4-dimensional. There is no 5th dimension. That is, until the dawning of the age of Aquarius, but that wasn't in 1919. So, where is this supposedly real 5th dimension for Kaluza and Klein? Rolled up. Now, if we think of each point in space, not as a little dot, but as a little circle that the unit vector placed there could move around, then we could account for both the gravitational and the electromagnetic forces at that location. Einstein himself pursued Kaluza-Klein type ideas, hoping that these extra dimensions might be the trick for restoring determinism to the universe. Right? He thought that maybe the reason quantum mechanics seems probabilistic is that the deterministic goings-on happen in this invisible extra dimension. Once we realize this, we'll be able to start looking closely enough at the world to find it, and determinism will be restored. Unfortunately, it failed. Wolfgang Pauli, the great Austrian physicist, thought that a Kaluza-Klein picture could unite the weak and strong nuclear forces. Unfortunately, this too failed. Right? With these failures, the multidimensional approach was discarded. Yes, it was mathematically elegant, but its results didn't pan out, and worse, it seemed to violate Occam's razor. If the entire project in science is unification, bringing things together in a simpler way, why resort to a hidden extra dimension to do it? The basic move smelled fishy to some. But then, in the 1970s, it came back as string theory. Now, string theorists seem to have come up with a way to account for all 4 forces. Right? If we think of the points of space as small loops of string in the way that Kaluza and Klein pictured for electromagnetism, right? Space here is not smooth. It's not continuous, but it's made up of a collection of these tiny loops of string. These strings can move in place in very different but independent ways, right? That is, they can vibrate or spin in ways that don't affect the other sorts of movement, right? So think of a string, right? A loop of string spinning around. Now, it can also roll in on itself, right? This is an independent motion because it in no way affects the spinning, right? Now, I could take my spinning, rolling string and introduce a longitudinal wave. That is, a wave that goes up and down as it moves across the string. I could have another longitudinal wave moving in a perpendicular direction, right? I could introduce a compressional wave, a wave along the direction of the string. In fact, I could have these compressional waves moving in opposite directions. So, between my spinning, my rolling, the longitudinal waves, and the compressional waves, we've just pictured 6 different independent motions the string could be undergoing at the same time. If we think of these independent motions of the string as dimensions, then we have a rich Kaluza-Klein type model. In 1995, the American physicist Ed Witten showed that we could use these modes of string vibration to account for both quantum and gravitational effects if they have 11 distinct modes. That is, if we take reality to have 11 dimensions, 10 for space and 1 for time. This doesn't mean that we should be able to take 10 pencils and arrange them so that they're all perpendicular to each other. But if we think of space as made up from infinitesimal strings, then they would need to be able to vibrate in 10 distinct ways in order to begin to account for all of the field interactions we observe. Some theorists argued we should not think of the points of quantized space as strings, but as 2-dimensional surfaces, like the head of a drum. Right? Such surfaces could vibrate in much more interesting and intricate ways. Space is therefore not made of strings, but membranes. A string is a simplified membrane of degree 1, where a drumhead membrane is degree 2. Others extended the idea to take higher degree membranes, but then the image is lost, and so the term membrane was shortened to just brane, B-R-A-N-E. So, we now have physicists talking not only about guts and toes, but also brains. Right? Different theories utilize branes of different degrees. Wanting to speak generally about such theories, physicists would refer to arbitrary branes of degrees p, or as they like to call them, p-branes. The idea is that in the properties of these p-branes, we will find a way to unify all of the forces in the universe into one single picture of reality. So, do we live in an 11-dimensional world filled with p-branes? We don't know yet. The process of redefining reality by modern science continues, as will our discussions, when we begin to look for the relation between p-branes and human brains.